Hi friends, is my voice is audible to you? If my voice is audible and if everything is clear, please let me know, right? Okay, 1 second, 1 second. Right, brothers. I hope my voice is audible to you, right? Isn't it or not? Yes. If you are able to hear my voice and everything is fine, please let me know. Right. Okay. Before I start this session, I just want to say a very big hi to all of my brothers and sisters who are on the online. And I just want to convey one more thing. There is so much of free content is already happening in this Unacademy learning app. If you didn't install this one till now, I recommend you to install this Unacademy learning app even right now just after the class. Okay, right. And if you want to follow, I can also recommend you to follow me on this Unacademy learning app using this link which is given below. Today's the session is all about limit state of torsion, the theory and problems we will work out completely on the limit state of torsion, how to design for torsion, the theory and the problems we will complete today. Right, right. Some people will say like, sir, how to take, is there any paid courses there in an academy learning app? Yeah, I just want to convey there is a paid course is already there in an academy learning app for civil engineers. So you can get that paid course of GATE and ESE by selecting this target as GATE and ESE. After you select the target as GATE and ESE, there is in the main drop down menu. If you go to main drop down menu, there is a thing called plus codes. In that plus codes, if you click that plus codes, you are able to see a tab called get subscription. Get subscription means it is the paid code. So if you press this get subscription, it will show the payment. And if you want to get 10% discount on all the courses in an academy plus platform, then in such case you are bound to use this code VT10, right? So when you are able to use this code VT10, directly 10% discount will come to you. Moreover, it shows your trust on me. It will directly connect between you and me, brother. Right. So, if you had taken this subscription, then you will get taught from India's topmost faculty directly in Nan Academy Plus, and you will be given access for all the live classes and recorded versions for all the courses in your particular stream from India's best educators. Some people say, sir, today is my sir hydrology ka notes YouTube ka milega sir. Dear Saket Kumar, I am concerned only about structures faculty. I am only a structures faculty. So if you want to ask anything, you can ask me about the structural thing. But non-structures, I don't know. You can talk to the persons who are teaching that non-structural faculty. Who are the non-structural faculty in that you can just ask them. Okay, समझ में आया भाई साकेत कुमार? Right. So some people will also ask us, sir, please introduce yourself. I am Venkata Tilak Uppalpati. Some people call me as Venkata sir. Some people call me as Tilak sir. I completed my master's degree from University of Sheffield, England, and about to complete my doctoral degree, PhD also. My background of education is completely into structural engineering. So here also in an academy, I am going to teach or tackle only the structural engineering subjects ranging from engineering mechanics, strength of materials, structural analysis, concrete structures, steel structures, and finally to construction materials and management. Right. Previously, I worked as coming to this university. This university has produced six Nobel Prize winners. You can understand the research potentiality of this university. And moreover, this university ranking is always far better than IITs and IIC Bangalore. So that's the reason why I had done my master's degree there. And coming to my previous work experience, previously I worked as research scientist or research engineer in University of South Carolina in USA for a funded project. And I worked for that project as team lead also. And moreover, I previously worked as head of the Department of Civil Engineering for an engineering college in Andhra Pradesh. This is in India. So I have both local experience and global experience. Being a structural engineer, even till today, I am working as an independent structural design consultant. My duties are I personally give structural drawings to my clients and I give material testing reports to my clients. Being a structural design consultant, these are the two things I do, right? So coming to my teaching experience, I have totally 12 years of teaching experience. I had mentored more than lakhs of students, and I can say I taught this 12. I have experience of this 12 years teaching experience in GATE and ESE in different coaching institutes all across India. Right. Some people will say like, sir, okay, what is the code that I need to use to get 10% discount? I just want to emphasize again, you are bound to use this code BT10 to get 10% discount on all the courses in Unacademy Plus. Some people will also ask us before I move to the ask us like, sir, you asked us to install the Unacademy Learning app. Na? How to install that one? So go to Play Store and type this name Unacademy Learning app. After you type this name Unacademy Learning app in Play Store, you can install that one. When you are able to install this Unacademy Learning app, you are able to see a screen on the right hand side, which is in this way. I hope you are able to see the screen on the right hand side. So this right hand screen that has got the main drop down menu. So in this main drop down menu, you go to free courses. After you go to free courses and in the search button, you type my name, complete name, Venkata Tilak Uppalapati. When you type my name Venkata Tilak Uppalapati, then obviously my profile will be visible to you. When my profile is visible to you, brothers, you follow me. What are the advantages for you guys when you are able to follow me? Already free content that I had done in an Academy Learning app that you are able to access for free of cost. The upcoming free video lectures, free courses of mine, you are able to access. You will be notified. That is the second advantage. Third advantage, at the end of each and every session, as per Saket Kumar, especially the notes is available in Unacademy Learning app, not in YouTube. Generally, in YouTube, we won't provide any sort of notes. But in Unacademy Learning app for Saket Kumar, for every topic that we had taken, even for the free session also, we will provide the notes in the form of PDF. So that's the reason why I am expecting Saket Kumar just after this class, you download this Unacademy Learning app and you can follow us. And if you are interested, if serious aspirant of GATE and ESE, I can recommend you guys, especially Saket Kumar, to take the paid course by using this code VT10. Some people will also say like, sir, can you say once again how to take the paid course also? Yes, I will do that one. After you install this Unacademy Learning app, na, you keep the target as GATE and ESE. This is the goal what you want to achieve. You can keep the goal as GATE and ESE. In this main drop down menu, you go to plus courses. After you go to plus courses in this main drop down menu, here in this plus courses, you can see the terminology got called as get subscription. After you press this term, after you press this one get subscription, you apply referral code VT10 to get 10% discount. You apply this code, then you pay the remaining amount. Pay the amount or pay the fees like that, we can say easily. And this is how you can even purchase the course in an Academy Plus, right, or plus courses. And another way that you can follow me is by using this link. After you download the Academy Learning app, by using this link you are able to follow me. This link is clearly given here, right? Some people will say, sir, what are the advantages when we had taken this paid course, right? The first and foremost advantage is there are instant doubt resolution is the first and foremost advantage in addition to daily live classes. Which the free guys doesn't have this scope of this instant doubt resolution directly by the faculty. That is the first and foremost advantage. In order to crack any sort of in order to crack any sort of competitive examination, support of test series is required. So here also in Academy, we are providing the support of test series in terms of quizzes, mock test, daily wise test, grand test, subject wise test. So if you are able to write those tests, then you will understand at what level you people are when compared to the topmost students of an academy, and you can measure your performance in terms of marks. If you want to improve your performance, you can improve by watching more number of video lectures in that particular topic, and by working out more number of problems in that particular topic. Like that, you can definitely improve your performance. There is no doubt at all. And coming to the third advantage is there is no need to plan yourself, brother. All the plan we will provide by structuring the course. Even the underperformed student is also able to cope up with our lectures. We will not compromise with the number of hours. And if you are able to follow that course program, even by working out the test series, definitely we are pretty much sure like you are able to crack the any sort of competitive examination with very good rank. And coming to the fourth advantage is, let us suppose on one day Saket Kumar is not able to attend the classes. In such case, Saket Kumar will be given, will be provided with the same lecture, I can say, in the form of recorded version. And Saket Kumar can watch the same recorded version for n number of times, depending on the comfort of his device. Maybe he can access the same lecture from mobile phone, or maybe from tab, or maybe from PC or laptop, depending on his or her comfort, right? So making all these advantages that will make you ready to crack any sort of competitive examination with pretty good rank. Right, these are some of the topmost indicators that we have, and you can have a direct look at the app. And the courses will be taught separately in English medium and also separately in Hindi medium. So there won't be any language barrier also. Some guys are good in Hindi, they can watch those Hindi medium lectures. Some guys are good in English, those people can watch the English medium lectures or English lectures. So there won't be any problem of language barrier also. Some people will also ask us before taking, sir, in GATE and ESE, especially in civil engineering program, how many courses you people had launched? We people had launched 8 courses, brother. And out of that 8 courses, few courses are in English, few courses are in Hindi. And I can say few courses are long-term courses and few courses are short-term courses out of these 8 courses. As each and every month we are increasing, as each and every month pool of faculty are going to get add. So definitely I can say the number of courses that were launched will also get increased. Definitely, there is no doubt. When you had taken the subscription, you will be provided access to all the courses that were launched by an academy in your particular stream, especially in civil engineering, like that. Right. So coming to the financial terms, for 12 months course, the cost after 10% discount is 27,225. If I can recommend this 12 months course and 18 months course for final year students. Final year students. If you are a student of third year or second year, I can recommend you guys with this 24-month subscription. So you are able to watch the same recorded versions or maybe live courses for 24 months, definitely, and the cost is around 39,600 after 10% discount. For any of the courses from 1 month course to 24 months course, you are bound to use this code VD10 to get 10% discount, brother, for any all the courses. So every day if you come to YouTube classes, every day my class is happening in this Let's Crack Gate and ESE Civil YouTube channel. My class is happening by 11 a.m. My classes are happening in structural engineering program. So for this month I am working out on RCC. I just want to convey one more thing. So please subscribe to our Let's Crack Gate and ESC Civil YouTube channel so that we can do more free content for you. And please share this video, like this video, and subscribe to our channel also. Don't forget to press the bell icon, brother. Please share these videos to more of your friends so that they will also get benefited. At least for free of course, they will get all these video lectures. Na? So please say the same thing to your friends. They will also get benefited. And moreover, to solve your problems, to solve your queries, I already started a Telegram group, and the name of that Telegram channel is Unacademy underscore Civil Engineer Tilak. And if you want to come down to that channel, you use the link which is given below. If you come down to that channel, if you are able to post your doubts, I will take care of your doubts in that channel. If it is structural engineering, if it is a non-structural doubts, the other faculty in that channel will resolve your doubts of non-structural part. Okay, right. Shall we start the session, brothers? One second. Right. So shall we start the session? In your previous class, if you had seen, we completed how to design for shear reinforcement. In case of beams, we had seen. The today's session is limit state of torsion, right? So what you will see in this today's session, you will learn how to design for torsion in case of beams. When the beam is subjected to torsional moment, how we will design the beam for torsion, that you will see here today. So before reaching the limit state of torsion, I can say the element is able to resist all the torsional moments. That's what I can say, right? So when this torsion is, so before I start this limit state of torsion, let me write here. Let me, one second, or can say limit state of torsion. So first of all, before I go to this torsion design, I just want to convey what is torsion. What is torsion or torsional moment? Torsional moment is a moment which is acting about the polar axis of the cross section. It is the moment acting about the polar axis of cross section, or in other words, how you can mention the same thing, or it is the moment acting with respect to the longitudinal axis of the member, right? Longitudinal axis of member. That's how we can define torsion. If you take, these are the cross sections, brother. This is the cross section. This is the cross section. This limit state of torsion, I am talking in flexural members. What are flexural members, brother? Flexural members are completely beams. Maybe if I want to show in 3D mode, I can show the 3D mode of the beam. This is the cross section. This is how the length of the beam is. I am not interested about the length of the beam. And the load here, this is P. This load P is acting as the transverse load, definitely, and this is eccentricity E here. And if this cross section is a rectangular cross section, this is the cross section is inverted L section, I can say, inverted flanged beam, I can say, in another words, flanged beam. Can I write in that way, flanged beam? And it is an inverted L section, or an inverted angle section, right? Like that, this cross section of RCC are there. This is how the beam is, and the loads are acting maybe for your convenience in this way. This is how the loads are acting. If you want to show here, the loads are acting. This is how in this. Right. Now, when this torsion is developed on the cross section, brother, when the torsion is developed on the cross section, I can say if the line of action of the force, if this is the force, this is what is the line of action of the force, right? If this is the line of action of the force, right? When the line of action of the force is not passing through the shear center, then I can say then torsion develops, then torsion develops in addition to shear force and bending moment. I hope you can see this is the shear center for this cross section. So what is shear center for a cross section means? It is the point through which resultant shear force is acting on the cross section. That point is nothing but called as shear center. Where you learnt about the shear center, brother, in your strength of materials, your teacher might have teach you how to locate the shear center for different cross sections, right? So especially when it is a symmetrical cross section, the shear center coincides with the centroid. So here this is the centroid of the cross section. So here for this shows here, yes stands for shear center. The shear center coincides with the centroid because it is a symmetrical, because here this is a symmetrical section. I hope you are able to see. Now this is the shear center. Okay, now the question is, sir, this is the shear center, sir. Okay, this is the plane of shear center, I can say in this way, right? But this is the plane of loading. There is some eccentricity between the action of the force and the shear center, right? So because of which, about this axis, I hope about this polar axis of the cross section, what is this axis is called as, about the polar axis of cross section, there is a moment which is p, right? This is p. So if this reaction will also pass through the shear center p, and if I take this p force effect here, two equal and opposite forces p into eccentricity e, so here definitely I can say on this cross section about this polar axis, here definitely a moment has got developed, and this moment is acting about the polar axis of the cross section. That's the reason why that moment is nothing but a twisting moment or torsional moment, which is P into E. So that means to avoid torsion, generally how I need to select the cross section, so that the applied transverse load, because why I'm saying transverse load, because it is in case of flexible plate, so that the applied transverse load should pass through the shear center. If it is not passing through the shear center, then in such case, likewise, definitely some torsional moment will also get developed. In such case, for the cross section, you need to design for shear force. In addition to shear force bending moment, you need to design for torsion also. Now I just want to say, so some people will say, sir, how to identify the shear center for this flanger section? Generally, the way of shear force distribution is from shear flow will be from downwards to upwards in this way, right? This is the direction of shear flow, right? If you take this moment of the resultant shear flow about this point, the resultant shear flow moment about this point is zero. So this will be definitely the shear center. Now above from this point, yes, the applied transverse load, maybe the p as point load, or maybe udl, I don't want to comment, that there is some difference between, there is some distance, or there is some gap, or I can say the shear center is not coincide with the transverse load line of action. So because of which, about the polar axis, here definitely, about the polar axis, definitely you can say some moment has got that developed. The name of that moment is torsional moment, which is p into e. So that's how the torsion is generally developed, brother, right? Now everybody will also ask me a question, sir. Okay, this is fine. So can you tell me what, in which cases, generally in which case of structural element torsion will get developed? I just want to convey you example, torsion examples where the torsion has got developed. If you take, this is the this is the axis of the member, this is the axis of the member, this is the axis of this ring beam of a circular water tank. This is the ring beam of a circular water tank. If I had shown in plan, these are I hope these are columns, whatever I am completely feeling, these are columns, right? If you take a ring beam, if you take a ring beam, a small ring beam, this small ring beam, if I had taken, right, this is how the ring beam is, where the if you had taken the ring beam, and this is the, and this is the centroidal axis of the member, this is how the centroidal axis of the member, where the load acting on this ring beam will be there, the total load will be acting on this entire ring beam here. So if I take this load as this point, there is some gap between the shear center and the point where the total load has got applied. This is the eccentricity. So because of this eccentricity here, definitely about this axis, definitely some torsional moment has got developed, because in this is in plan. This is in plan. If you take if this is in plan, if I cut the section here maybe, then definitely I can show this is how the cross section will be. So about this axis, definitely a moment has got developed. And what is the name of that moment? That moment is nothing but torsional moment. So first example for torsion is in case of ring beams of circular water tank. And second example is beams that are curved in plan. Where you can see the beams that are curved in plan. I hope you can say beams that are curved in plan. Please understand. So this is plan in sense beams curved in top view. Where you can see the beams curved in top view. I hope in case of water tanks only you are able to see a curved beam in plan. In case of a water tank, generally if the beams are curved in plan. In these cases, you are able to see the cross section of the beam is subjected to definitely some torsion. This is the eccentricity here we can say. Now the third example is in case of isolated L beam. Let us suppose what is an isolated L beam. If a single beam is supporting the slab, then in such case it is an isolated beam, right? Can I write that one? if if a single beam only is supporting slab, then the beam is called isolated beam. Isolated, we call it as isolated beam. Okay. Now okay, here if I take this is the slab, this is the beam. Okay, now this is in front view. I just want to convey front view. This is isolated beam in top view. This is how the beam is running, and this beam is running between two columns here. These are the two columns between which the beam is running, which is supporting this slab. Okay, where the slab load will happen, brother. So the entire slab load will get concentrate at the centroid of the slab. This is the centroid of the slab. This is how the entire slab load will act here at this point. If you take this is the axis, this is the centroidal axis of the beam member. So between the centroidal axis of the beam member and the applied load, there is some eccentricity is there. So because of the eccentricity, we can say here definitely with respect to this axis is nothing but a longitudinal axis of the beam. So if I want to show you the same thing, this is how maybe it may run. This axis is nothing but a longitudinal axis of the beam. Or for the cross section here for this member, for this cross section of this member, this axis is also called as polar axis of the cross section. Both are one and same. Right? Both are one and same, right? Okay, right. Some people will say like, sir, okay, both are one and same, which is fine. Now the question is, these are the examples for torsion you told. Okay, now you tell me, is there any other examples for torsion is there? Yes, I want to show more examples for in which case the torsion is dominant. I want to show you that, right? Yes, I want to show you this case, especially here. In case of connected beams, in this way, end beams, these are intermediate beams. T beam is an intermediate beam. and these are end beams. These end beams, in case of in connected beams, end beams or edge beams are subjected to torsion or are subjected to torsion. I hope you had seen in this connected beams, the slab and the beams are made monolithically or constructed monolithically. In connected beams, in connected beams condition, both the beams and slab were constructed monolithically. When these were constructed monolithically, then in such case you can say the end beams act as an L beam. I hope this is the end beam. I can say some part of some width of slab will act in unison. Some width of slab will act in unison uh, with the beam. So the beam behaves as a so the beam behaves as a flanged beam. So that's the reason why I had shown this end beam is not a rectangle. I had shown this end beam as a L beam here. Because some width of the slab will act in unison with this rectangular beam. So the behavior of the beam is just like that of an L beam. If you take this L beam, for this L beam, this is the shear center, brother. I hope you know. This is the shear center. This is the shear center, or this is the centroid. This is through this plane. This is the centroid of the element, right? But here the loads will act. Maybe this is how the load will act between the load and between the shear center. There is between the applied load and shear center. There is eccentricity is there. So because of which, in case of connected beams, especially for end beams or edge beams, definitely torsion will get developed. And one more thing, what is the other example for torsion? I hope in some of the cases, especially in case of connected beams, you might had seen like these are all columns. So and there is a beam which is these are the main beams. What are main beams? From the main beams, the load of secondary beam will be distributed to column. That beam is nothing but main beam. So this is main beam 1, main beam 2. Between these two, how the load will be distributed from the slab on the main beam? The load will be distributed from the slab on the main beam by using secondary. This is secondary beam. Now you can see some people will also ask us, sir, how the load distribution will happen from beams to from slab to beams and beams to columns. I just want to convey you with the help of from slab load is taken care by secondary beam. From secondary beam load is distributed as point load on primary beam. So primary beam, the load is distributed to column. From primary beam, load is distributed to column. So now you can see how the load is transferring here, brother. The load is transferring here. Definitely, I can say the load is definitely transferring here. The slab, if you take here a slab is there, brother. If you take here a big slab is there, because of that slab load, the secondary beam is bending, right? due to slab load. Secondary beam, I hope you can see, you are able to see this secondary beam will bend, right? Let me show you here. This secondary beam will bend because of monolithic construction between the secondary beam and primary beam here and here. Definitely some moments will get developed, right? So if you take 1 second, if you take these what you call this axis and this axis, okay, if you take this axis, so if you take this member from m1 to this secondary beam, because of the secondary beam will apply a moment on the primary beam here in this way. Because of secondary beam will apply a moment on the primary beam in this way. What are these moments are called as, for this axis, or if you take for this axis, these moments are torsional moments. That means how this torsional moment has got created in case of this spandrel beam, brother. In case of this spandrel beam, the torsional moment has got developed because of bending of the secondary beam or spandrel beam. Torsion is developed in primary beam. Like that also torsion will get developed, right? Is that okay? Can I move to the next slide, please? Can I move to the next slide? Right. Some people will say, sir, is there any other example where the torsion will also come? Yes, I just want to show you the example. Torsion is also possible in case of slabs. In case of slabs, in case of slabs, in case of two-way fixed slab, if there is a slab is there, if the beams are running here in this way, beams are running in all the four directions in this way. You can say 1, 2, 3, 4, and here also in this way. If the beams are running in this way, now the question is, okay, the beams are running in this way, especially if you take the corner slabs. I hope you can say what are these corner slabs. If the torsion is developed at the corner of two-way fixed or restrained slab, torsion is developed at this slab, at this slab, at this slab, at this slab. So if you take the torsion at the corner of a two-way fixed slab, maybe I can say, show you right in this way. Hmm. I can show you here clearly. If you take this slab here, there is the loads on these beams. If you take this beam and this beam, right, the loads acting, this is the axis for the beams here. The load is acting here. About this axis, the load will provide a will develop a moment on this beam here. The load will develop a moment on this beam here in this direction. So which will make you at this corners, at this corners of this two-way fixed or restrained slab, when the slabs are restrained, and these are discontinuous edges here. These are discontinuous edges. So at the discontinuous edges in cases of slab, at discontinuous edges in case of slab, at discontinuous edges in case of slab, I can say torsion will develop when the slab is restrained to rotate, right? So in such case, this is possible, right? Now everybody will also ask us, sir, you had told different examples in which case the torsion will get developed, right? Now the question is, sir, how to design for the torsion? That is the big question. So how you can design the torsion? So if you see IS 456, even if you see IS 456 2000 code, IS 456 2000 code has advocated like there is no separate design for torsion, but in case of when torsion is dominant, then in such case biaxial bending is possible, na? When torsion is dominant, skew bending or biaxial bending is possible. So what this IS 456 gives is there is no separate design for torsion. As per the scientist named as this IS 456 2000 has advocated to use the theory which is proposed by scientist HSU. HSU is the name of the scientist who proposed the theory of skew bending. So based on this theory, he has given some guidelines how to design for torsion. So what is that HSU theory? Even in IS 456, the same HSU theory was used for the design of torsion. As per the scientist HSU, there is no separate design for torsion. First of all, you should understand. So I can say there is no separate design for torsion. Some part of the torsion, if you take some torsional moment, is acting on the cross section. Let us suppose because of this torsional moment, which is equal to P into E, I can say some part of the torsion is added to bending moment. So if the torsion is there, in order to resist this torsion, already about this x-axis there is some bending moment. Maybe I can say mz, and there is a shear force which we people call it as maybe v. So in order to design for this torsional moment, which is equal to torsion moment, which is equal to T is equal to P into E. The some part of this torsion has got added to this bending moment. Some part of this torsion has got added to the shear force. So by increasing the design bending moment, by increasing the design shear force, by using this HSU theory for that increased or exaggerated bending moment, for that increased or exaggerated shear force, if we design the cross section like design for shear and design for bending moment for the increased bending moment and shear, if we had designed the cross section, in such case that cross section will be safe even in terms of torsion also, like that HSU has proposed, right? So I can say is added to shear force, is added to shear force, and other part, some part is added to shear force and some other part is added to the bending moment. With increased shear and bending, the beam is designed for increased shear force and bending most, the beam is out of this shear force and bending mode. Shear is the primary criteria and bending moment is the secondary criteria. Some people will also ask like, sir, why can't be the bending moment is the primary criteria, why why can't the shear is the secondary criteria? Dear brother, maybe from your strength of materials program, if you see from strength of materials, then torsion is acting on the cross section. When torsion is acting on the cross section, the nature of stresses developed are, what are the nature of stresses that are developed? The nature of stresses that are developed are shear stresses in nature. The nature of stress developed in cross section is shear stress. So how you can say that once everybody will say like, I hope from you from torsion formula, because of pure torsion, this is the formula T by polar moment of inertia is equal to shearing stress by R, which is equal to J theta by L. So from this pure torsion formula, you can understand when torsion is dominant, then by the time shear stresses are dominant, not the bending stresses. So based on that one, the primary way of failure because of torsion is shear. The secondary mode of failure because of torsion is bending failure or flexural failure. Now, if I want to design for torsion, what is the data that will be included, brother? Can I rub the screen, brother? Can I rub the screen? Right? Saket Kumar ji, Vasant Sai, can I rub the screen? Right? So coming to the data that includes, what is the data that was included here, brother? What is the data that will be included or given in the problem? Data that is given or included in the problem is torsional moment, where TU stands for factored torsional moment. EMU, factored design bending moment, factored design bending moment. And VU, it is factored critical shear force, factored shear force maximum value, right? And I hope B, what is this B? Width of the beam. What is capital D? Overall depth of the cross section, right? Overall depth of cross section. And after this one, if I know the cover to reinforcement, like clear cover or effective cover, clear clear cover or effective cover to the reinforcement, something will be given, clear cover or effective cover to the reinforcement, then I am able to work out the effective depth of the section. D is effective depth, which is equal to overall depth minus effective cover. And they will give you FCK, the grade of concrete. They will give you F5, the grade of steel. They will give you tau C max, maximum shear strength of concrete, maximum shear strength of concrete, or limiting shear strength of concrete indirectly. What is tau C? That is the shear strength of RCC beam with percentage of tension steel. Shear strength of RCC beam with the percentage of tension steel. This is how we can do. Now, right, let me explain you. These are the parameters that were given. Now the question is, sir, what is the design for procedure for torsion? You asked us, we need to increase the bending moment. We need to increase the shear force to higher value. Now, so what is the equivalent shear force for which I need to design the cross section? What is the equivalent bending moment for which I need to design the cross section? The primary one here it is, the primary one in the design of torsion is shear force design. Secondary one is bending moment. I mean, the second one is flexural design. So let me talk about the shear design for increased shear force. What is the equivalent shear force for which we are designing the cross section when torsion is dominant? I want to teach you that. Is that okay? Can I move to the next slide? Can I talk about the next slide, brother? Yes. So coming to the step number one. In this step number one, I need to find out equivalent shear force. The equivalent shear force is the total shear force which is due to external loads and due to torsion. Total shear force which is due to external loads. Due to external loads, it is nothing but VU. But shear force due to torsion. So due to torsion, which is nothing but VT. So VU will be given to you. This is known or given. So at this VU, some people will say like, sir, for projects, how we can work out this VU? I just want to work out for projects. We are able to work out the critical shear force. So find shear force at critical section. In your previous class, especially limit state of shear, what is the critical section for shear? When the supports are under compression, when the supports are under tension, especially I had mentioned. So at that particular section, what is the shear force that was there? You please try to work out that one. So generally this VU will be given, right? So VU. And coming to VT, what is the shear force because of torsion as per HSU theory? As per HSU means there is don't think any other way. HSU is the name of the scientist. As per HSU theory, or another way, this guy has the proposed the skew bending theory, or skew bending theory, or as per skew bending theory, the shear force that is coming into picture because of torsion or due to torsion is 1.6 times of torsional moment TU, factor torsional moment by B. So I hope you know TU stands for torsional moment, factor torsional moment, factored torsional moment. And B is the width of the beam. P is the width of the beam. So based on these two, you are able to work out the equivalent shear force. After you work out the equivalent shear force, first of all, you need to design for shear. To design for shear, first of all, I worked out the equivalent shear force for which I need to design the shear reinforcement. After I work out that one, the remaining steps are just like that of limit state of shear only. In limit state of shear, after you work out the shear force, what you will work out, you will make a comparison between tau b and tau c. Here, what is the nominal or average shear stress because of this equivalent shear force? Nominal average shear stress due to equivalent shear force that you already know. So tau v is VE by this is shear area. I can say if it is a rectangular section, the shear area is B into D. If it is an L beam or for flanged beams, I can say, right, for flanged beams, for L beam or for flanged beams, this B is nothing but breadth of the web, because I mentioned it is shear area. Shear area is generally the uh, area of the web. Generally, we can write in that way, isn't it or not? So when tau, there are three conditions are there. When tau VE is less than or equal to, condition number one, when tau VE, that is a nominal or average shearing stress due to loads, is less than or equal to zero point 0.5 times of shear strength of RCC beam. What is tau C stands for? It is the shear strength of RCC beam for a desired percentage of tension steel, that was for a percentage of tension steel and FCK, right? So this will be, if you want to see the same thing in terms of code of practice, refer table 19 of IS 456. But generally in your competitive examinations, they will provide this value of tau c. In this case, in this particular case, the cross section is safe in shear when tau b is less than or equal to tau c. In this particular case, the cross section is safe in shear, and there is no need of even minimum shear reinforcement is required, where you can see this type of structural elements, in which case this type of things are happen. This type of things will happen for structural elements like sunshade, chajja, portico, or slabs. Generally, if you take these things, these are the examples where we don't provide even minimum shear reinforcement also, because the case is the developing shear stresses, average shear stresses are less than 50 percentage of the shear strength of the RCCB. In such case, not even minimum shear reinforcement is required. Now some people, especially Saket Kumar, will also ask us, sir, okay sir, now you tell me, let us suppose, sir, when the developing nominal or average shearing stresses are more than 50 percentage of shear strength of RCCB, but less than shear strength of RCCB. In that case, like if if tau VE, it is the developing or average shear stress, average shear stress developed, if average shear stress developed is more than 50 percentage of shear strength, of RCC beam, right? Is more than 50% of shear strength of RCC beam, but less than or equal to shear strength of RCC beam. In this case, I can say the cross section is safe in shear, okay, but I need to provide minimum shear reinforcement. Need to provide minimum, but I need to provide minimum shear reinforcement is required by vertical stirrups, by required in the form of vertical stirrups. By vertical stirrups only, I need to provide that minimum shear reinforcement. Now, everybody will also ask us, sir, how to design for this minimum shear reinforcement. This is just like this is the equation, just like that in case of equation used for minimum shear reinforcement spacing. Equation used for minimum shear reinforcement spacing. So this is how from this equation we can work out. Generally, here the design of shear reinforcement means we need to fix the stirrup diameter. If we had fixed the stirrup diameter, like phi diameter of the stirrup is 8 millimeter and it is two-legged stirrups. If I say two-legged stirrups, then this ASV, cross section area of the shear reinforcement, I can say n into pi by 4 into phi square, and the two-legged stirrups means the value of n is actually 2 and the value of phi for this example of diameter of stirrup is 8 millimeter, 8. So that means I know this ASV. I know this ASV. The width of the section is known to me. Zero point 0.4 is known to me. Fy is yield strength of stirrup reinforcement or shear reinforcement. Yield strength of shear reinforcement. So if you do this one from that one, the one and only unknown is SV. So from this equation, can you work out SV or not? After you work out the spacing of this shear reinforcement, the SV is unknown to us. After we work out this SV cannot be more than 0.75 times of D and SV cannot be more than 300. These are the conditions I need to use. I need to use the minimum of these three. Yeah, out of SV, out of 0.75 times of D, and out of 300 millimeter, I need to use minimum of these three. I need to use, right. So SV I had worked out from this above equation, right. Now this may be case two. This may be the previous one. Maybe I can say as this may be case one. There is a third case is also there, like when the developing nominal or average shearing stresses are more than shear strength of RCCB. When tau v, this is case when tau v developing equal developing average shearing stresses are more than shear strength of RCCB. In such case, what is the conclusion that we can go for? The conclusion that we can go for is it is not safe in shear. So the cross section is not, I mean, the beam is not safe in shear. Beam is not safe in which mode? In shear mode. So in such case, I need to design the shear reinforcement definitely. So shear reinforcement is required. Shear reinforcement design is required. Providing shear reinforcement design, or I need to design the shear reinforcement is required only in the form of vertical stirrups. Here also only why vertical stirrups. As per IS 456, there is one more clause is there. If you refer to as per IS 456 2000, right? If the cross section is subjected to torsional moment, then the design for shear reinforcement, whether we are providing for minimum shear reinforcement or design shear reinforcement, the shear reinforcement must and should be in the form of vertical strips. If the cross section is subjected to torsion, then shear reinforcement, I can say, then shear reinforcement, then shear reinforcement should be in the form of vertical stirrups. Why only vertical stirrups? Because these vertical stirrups are more stable in form work than inclined stirrups. Inclined stirrups are good in resisting shear, but the major problem with respect to inclined stirrups are not stable in if you take in form work. Those inclined stirrups we may come as vertical stirrups, or it may bend, or it may tilt also. So that's the reason why, especially when the torsion is dominant, by the time the code says you design the shear reinforcement only in the form of vertical stirrups. And as per IS 456, inclined stirrups and bent up bar should not be considered when the cross section is subjected to torsion. So that the same reason, right? So now everybody will also ask us, for which shear force? Okay, I need to design the shear reinforcement. For what shear force I need to design the shear reinforcement in the form of vertical stirrups? That is the question. Now let us suppose you understand from a common thing. If the shear force acting on the cross section is 100, it is total shear force out of 100, 25 kilonewton is the strength of RCC beam. Then for what shear force I need to design the shear reinforcement? The answer is very simple. For the remaining 75 kilonewton only, I need to design the shear reinforcement, right? So in the same way, design shear force for shear reinforcement, which is we people call it as VUS. VUS is equal to VE, that is the equivalent shear force, minus this is the shear strength of RCCB. Shear strength of RCCB in Newton or kilonewton. Actually, tau c itself is shear strength of RCC beam. The tau c multiplied by shear area will give me the shear strength of RCC beam in newtons or in kilonewtons. Then definitely I am bound to get this VUS. After I work out this VUS, some people will say like, sir, how to design for vertical steps? I just want to convey for if the design is by using vertical steps. Generally, people think like the what is the formula that I had used for a limit state of shear. The same formula here I will use. No, no, no. This is the formula that I had used for limit state of shear. Okay, in limit state of shear it is used. In limit state of shear it is used. But when cross section is subjected to torsion, this formula is not applicable if torsion is acting. In such case, what is the thing generally I need to use for to fix the spacing? To fix the spacing in such case, I need to use this equation which is below. But this type of question will not be asked in competitive examination because it is a lengthy formula, na? And moreover, it is not usually asked for competitive examinations. But let me define ASV. I hope, do you know ASV or not? ASV is the cross sectional area of shear reinforcement. N into pi by 4 into phi square. This is known to me. SV I don't know. Fi yield strength. Some people will say like, sir, how, what is this B1 and D1? If this is the cross section is in this way, brother. The cross section is in this way, right? We had provided the main reinforcement. Maybe I can say the main reinforcement is in this way, right? And after this main reinforcement is provided, if you see, or if you want to see the stirrup reinforcement, this is how, okay, 1 second, this is how the stirrup reinforcement will be provided. Maybe this is how the stirrup reinforcement was provided, for example. So here B1 stands for this dimension, in between which the width of the stirrup leg indirectly. B1 stands for width of the stirrup leg, and D1 stands for the depth of the stirrup leg. Here this is D1. So we are able to work out B1 and D1 directly from this figure itself. So B1 is known to me and D1 is also known to me. So B1 known, D1 known. And what is Fi? Fi stands for yield strength of the shear reinforcement. Generally for shear reinforcement, the yield strength is mild steel only, na? So maybe the grade of the mild steel generally we are using. This is also known to be. And you know TU, what is the torsional moment acting on the cross section? What is the shear force acting on the cross section? You know this one. So from this equation, you are bound to work out the one and only unknown called as spacing, right? You are able to work out this one, but this question will not be asked. Now, the theory part is over, brother. So some people will say like, sir, what is the best section to resist torsion? The best section to resist the torsion is, I can say, hollow sections. So especially you might have seen the hollow sections in case of girders, especially I hope you know for metro rail projects, for metro rails and for bridges, you might have seen a hollow section. Because of this hollow section, with lesser cross-sectional area, higher moment of inertia is possible. Higher polar moment of inertia is possible for hollow sections with lesser lesser cross-sectional area. One second. With lesser cross-sectional area, higher polar, because the question in the applied one is torsion. To reduce the torsional stresses, if you see the torsion equation, T by Ip is equal to Qs by R. If I want to reduce this developing shear stresses because of torsion, then Ip value, polar moment of inertia, should be higher. Generally for this box cutters, generally for these hollow sections, especially I can say, for hollow sections, generally with lesser cross sectional area, higher polar moment of inertia is possible, right? This, yes, Shivam Tiwari, I am able to see your comments. Shivam Tiwari, I am able to see your comments. I am able to see your comments. Box section. Maybe I cannot say simple box section. Any type of hollow section. Example for hollow section is box cutter. Okay. Maybe you can go for sometimes the box cutter can also be in this form. Maybe this is also a box cutter. This is how you might have seen the box cutter shapes also, especially for metro rails maybe, or for bridges you might have seen this type of stuff. Because for these types of cross sections with lesser cross sectional area, the moment of inertia about this axis may be ZZ. The moment of inertia about YY. Oh, one second. Let me show with another color, brother. About YY, when moment of inertia Iy is increasing, Iz is increasing, polar moment of inertia about this x-axis, maybe Ix, which is polar moment of inertia, which is Ix is equal to Iz plus Iy, this value will also get increased, right? So that's the reason why the best section to resist the torsion is, I can say, is hollow section, right? Right. Some people will also say like, sir, okay, some one more theory question is also there. Like some people will say like, sir, if I take a pen, if I take a pen or if I take a rod, if I take a rod after the rod was subjected to torsion, sir, if it is subjected to torsion and if the material is brittle material, if it is a brittle rod or I can say brittle chalk piece, brittle material. Example is chalk piece. I hope you know chalk piece. In case of brittle material, when it is subjected to torsional moment in this way, what is the way, in what direction the cracks will happen? I just want to convey you, especially due to torsion, the way of failure is mostly by shear failure. So shear failure, and here it is because of torsion. Brittle material cracks due to torsion, and the cracks are in. I hope you are able to see the cracks are completely in spiral way. I hope these are in spiral way. If you want to check, you can take a chalk piece, try to twist it. Try to twist a chalk piece because chalk piece is a brittle material. Take a chalk piece and try to twist it. How the failure will be? The failure of the chalk piece will be, you are able to see in this way. So which is a spiral way of thing, and the angle at which this crack is happening, spiral at an angle of 45 degrees. So this is how the cracks will form in case of brittle materials because of torsion, right? Now some people will also say like, sir, you tell me how many number of steel bars are kept in beam. Generally, the minimum number of steel bars that are kept in beam, the minimum number of steel bars that are kept in beam, these are four number of steel bars that are kept in beam, brother. Minimum. This is the minimum number of steel bars that are kept in beam. One steel bar should be kept at each and every corner here like this. So minimum at least I need to provide four steel bars, one at each and every corner. So in case of beams, right, right. Some people will say like, sir, okay, the theory part is over. Now, before I end up the theory part, some people will also ask us, sir, you teach us how to design for shear when torsion is coming. You didn't teach us how to design for bending moment, how to design for bending moment when torsion is coming into picture, right? Everybody will ask that, right? Hi Shivam Tiwari, yeah. So I hope you are able to see. Previously I already mentioned, if you remember or if you don't remember, when the cross section is subject to torsion, there is no separate design for torsion. The cross section will be designed for increased shear force and increased bending moment. I teach you how to design for shear force, how to design for the cross section because of increased shear force, right? I didn't teach you how to design for cross section because of increased bending moment, isn't it or not? Now, for to work out that one, before I work out that one, I just want to convey one thing. Due to torsion, the primary failure is shear, whereas bend flexural failure or failure due to bending moment is secondary, right? I can write in this way. Now the question is, sir, for what increased bending moment? What is the increased bending moment I need to consider for the design of the cross section for flexor especially? So in if you take a cross section in the design of flexor, there are two elements are there. One is area of tension steel design is separate and area of compression steel is design is separate. If I want to design for main reinforcement, area of tension steel, how to design for main reinforcement in a beam with torsion, AST, area of tension steel, right? Let us suppose, now I want to know you. I hope you know tau VU. Tau VU, what is tau VU? It is the average nominal shearing stress developed. It is the equivalent shear force divided by BD. And I hope you know the equivalent shear force, which is VU plus 1.6 times of TU by BD. This is known. So this is known to you. And tau C, it is the shear strength of RCC beam. This will be given in the problem. This is already know, or you can work out the same thing, the tau C from table number 19, which is a function of FCK, grade of concrete, and percentage of tension steel. So if tau V is less than tau C, in such case no shear failure will happen, right? Generally the concept is no shear failure. When there is no shear failure, the primary one is shear failure. Now when shear itself is not failing, then the design bending moment I cannot need to get increased, right? Then the design bending moment is the bending moment just because of external loads in itself. There is no increase in the bending moment I need to consider in that particular case. What is in such case the design bending moment is MU. What is that MU stands for? MU stands for the bending moment because of external loads. So how you can work out this bending moment because of external load? Generally, in your competitive examination, this will be given. If in case of project, this design bending moment because of external loads, we can work out. I hope from structural analysis program, you know how to find out maximum bending moments in a framed structure, right? This is maybe I can say for main reinforcement. This is why how I can say this is case one. And I already teach you how to design for tension reinforcement when the design moment is known to you. This we can work out from limit state of shear. The tension reinforcement AST we can work out from limit state of flexor, I can say. So I can say after you know the design bending moment, we can work out AST from limit state of flexor. Limit state of fracture. Now, some people will say like, sir, this is case one. Let us suppose there may be another case is also possible, sir, like case two. What is that case two is when the developing or average shearing stresses because of equivalent shear force is more than the shear strength of RCC beam when tau V is greater than tau C. In such case, the design bending moment for area of steel is that this is the design bending moment I need to consider. The design bending moment is bending moment because of loads plus bending moments because of torsion. Due to load, bending moment due to loads, which we people called as MU, bending moment that is coming into picture because of torsion. I can say uh, bending moment developed due to torsion. Can I write in that way? Can I write which is MT? Is that okay, brother? This is how you can say. Okay, this is MU. We can work out from the structural analysis program. Everybody right now will also ask us how to work out this bending moment because of torsion. If you refer to HSU theory or skew bending theory. So after referring HSU theory, I hope HSU is the name of the scientist. Don't think in another way. HSU theory or skew bending theory. they proposed they proposed this equation for bending moment that is coming into picture because of torsion, and the answer is tu into 1 plus d by b divided by 1.75. What is tu stands for torsional moment factored torsional moment. What is d? Overall depth, everybody knows. And what is b stands for width of beam. So like that, we are able to work out this design bending moment. Now everybody will also ask us, sir, you had teach how to design for main reinforcement. What is the design bending moment you teach for tension steel? Similarly, what is the design bending moment for compression steel? You need to mention, right? So let me, before I talk about that compression reinforcement, okay, let us work out the problems. After I work out the problems, I will teach the small class like what is the design bending moment that I need to use for the design of compression reinforcement. Okay, so please work out this, right? So I hope you are able to see this first question, right? Shivam Tiwari, brother Shivam Tiwari, are you able to see this first question? An RCC beam is of size 300 millimeter by 100 millimeter. Okay, it is there. 300 millimeter by 100 millimeter. It is subjected to 300 millimeter by not 100, it is 1000 millimeter. 300 millimeter by 1000 millimeter. It is subjected to a shear force of V is equal to 150 kilonewtons. And the bending moment at limiting conditions means it is mu, and t torsional moment at limiting conditions means it is tu. These are factored moments. Then what are the equivalent moment, bending moment and equivalent shear force at ultimate loads? So see, to work out equivalent shear force, how you can work out the equivalent shear force? VE is equal to equivalent shear force. How I can work out equivalent shear force? Shear force because of external load plus 1.6 times of tu by b. If you work out what is that vu, vu stands for, it is subjected to a shear force of v is 150 at limiting conditions. When it is at limiting condition, that shear force is vu. So I can say vu is 150 kilonewton plus 1.6 times of tu. What is the tu, brother? 30 kilonewton meter divided by what is the b? What is b stands for? The width of the beam. The width of the beam is 300 millimeter. But if you see the dimension of the dimension linear dimensions are in meter. So I need to write this value of b also in meter, so which is 0.3 meter. If you work out, it is 310 kilonewton. That means equivalent shear force is 310 kilonewton, no doubt. Now everybody will also ask us, sir, what is the equivalent bending moment, right? How I can write this one? Equivalent bending moment. So equivalent bending moment. Equivalent, to write the answer of equivalent bending moment, actually there should be some there should be, what I can say, there should be comparison of tau ve and tau c. When tau ve is greater than tau c, the equivalent bending moment has got one formula. When tau ve is less than tau c, then less than or equal to tau c, then equivalent bending moment is equal to just mu, right? So but to compare these two stuff, the tau c value is required. Tau ve I am able to work out here. Tau ve, how I can work out, which is ve by bd, we can do that one. But shear strength of RCC beam is required. To work out the shear strength of RCC beam, tau c, it's a function of percentage of tension steel and FCK, and I require table number 19 to work out, but no such data is given. So in such case, the equivalent bending moment, I need to I need to exaggerate it. What is the equivalent bending moment in that particular case? I can take, which is mu, that is the bending moment because of external loads, the bending moment because of torsional moment. What is the bending moment because of torsional moment? Which is mt, which is mu, plus what is mt bending moment because of torsional moment, which is tu, into 1 plus capital D by B divided by 1.7. This is how we can work out right now, isn't it or not? So can you work out this quickly, brother? Mu, what is the bending moment at limiting conditions? The bending moment at limiting conditions is 150 plus Tu, which is 30, into 1 plus D by B. Overall, what is the effective depth? What is that effective depth, brother? The overall B, this is B, this is effective, this is overall depth. Capital D is 1000 millimeter. Now, 1000 millimeter in terms of meter is 1 meter divided by B, width of the beam. The width of the beam is 300 millimeter. If I write in terms of meter, it is 0.3 meter, right? Divided by 1.7. So everything we will get everything in terms of kilonewton meter, because this mu is in kilonewton meter, tu is in kilonewton meter, d and b should also be in meter, right? If I work out this one, the answer is 226.47, 226.47 kilonewton meter. So what is the correct option, man? The first one is 226, because they are expecting equivalent bending moment. Second one is shear force, right? So equivalent bending moment is 226 and shear force is 310. Na? So the correct option is only option D for Detroit is the correct option. Is that okay, Shivam Tiwari? Right? Shall I work out the next question? Moving to the next question. I hope you are able to see, right? I hope you are able to see this question. Right. Before I want to talk about this one, I just want to say, like, they are expecting longitudinal compression steel shall be designed for a moment. What is the design bending moment here in this case? I just want to convey you one thing. What is the design bending moment? Design bending moment for compression steel. Design bending moment for compression steel. I can say here ASC, area of steel compression. ASC, which is compression steel, is also required if bending moment because of torsion is more than bending moment because of external loads. What is MT? MT stands for bending moment because of torsion. So that is when tu into 1 plus d by b divided by 1.7 is more than mu, then I need to work out the extra compression steel. What is the compression steel I need to design for in this case? The design bending moment, I can say. 1 second. The design bending moment here in this particular case is me2. The design bending moment for compression steel is mt minus m. Let us suppose there is one more case is there. If mu, this is maybe case 1 for compression steel, for case 2 for compression steel, for case 2 if mt is less than mu, in that particular case no need to provide any extra compression steel. No compression steel is required, I can say. uh, no no compression steel is required. Now if you see this problem, what is the bending moment because of external loads? That is mu is equal to 100 kilonewton meter. If ultimate torsional moment is tu is equal to 68 kilonewton meter, then can I work out mt? If I want to work out this mt, which is mt is equal to mu plus tu. Mt is equal to, I can clearly write here like mt is equal to uh, mt is equal to tu into tu into tu into 1 plus d by b divided by 1.7. So if I work out this one, what is the tu, brother? That tu is what is the value of the tu? 68 into 1 plus capital D. The overall depth is 600 millimeters. It is zero point 0.6 by zero point 0.3. Effective width is 300 millimeter divided by 1.7. It is 63 into 68 into 3 divided by 1.7. This is almost 120 kilonewton meter. The MT here in this present case, MT is greater than MU. When MT is greater than MU, what is the equivalent bending moment? What is the bending moment for which I need to design this longitudinal compression steel? So design bending moment for longitudinal compression steel, which is Me2, which is MT minus MU. The answer is 120 minus MU, it is 100. The answer is generally 20 kilonewton meter. This is the bending moment for which I need to design the extra compression steel, which is option A. Option A is the correct one, right? So can I move to the next slide or next problem, brother? Can I move to the next slide or next problem? Right, Shivam Tiwari? Right? Moving to the next slide or next problem. So coming to this next problem, I hope you are able to see this problem, brother. Right? At the limit state of collapse, सर डॉक्टर सिविल सर पर कब आ रहे हो सर प्लस पर कब आ रहे हो dear Dr. Civil, I just want to convey one thing. When they say to teach in plus, by that time only I can come down to plus. They didn't give any information till now to teach in plus. So जब जब वो मुझे बता देगा तब मैं आऊंगा, right? So please, Dr. Civil, right? So can you see this question, brother? So can you see at the limit state of collapse? I hope you can see at the limit state of collapse, the RCCB is subjected to total flexural moment. The total flexural bending moment, total flexural moment is bending design MU, which is 200 uh, kilonewton meter. Why I am saying it is factored bending moment? Because they are saying at limit state of collapse. That is the hint. And factored shear force, which is people call it as VU, is 20 kilonewton, and a factor torsional moment, which people call it as TU, 9 kilonewton meter. The beam is 300 meter wide, so B is 300 millimeter, and 425 millimeter gross depth. Gross depth means overall depth. Overall depth is 425 millimeter with an effective cover of, effective cover means D dash, effective cover is 25 millimeter. Then I can say effective depth of the section is overall depth of the section, which is 425 minus effective depth is 425. The answer for effective depth is 400 millimeter. The equivalent nominal shear stress, which we people call it as tau V, equivalent nominal shear stress tau V as calculated tau VE, they are giving a hint like the equivalent nominal shear stress tau VE as calculated using the code turns out to be lesser than tau VE is less than design shear strength of the concrete. Tau VE is less than tau C. Then by that time, what is the equivalent shear force? The equivalent shear force, whether it is tau VE is less than tau C or maybe tau VE is greater than tau C, for any case, the equivalent shear force is directly equivalent shear force VE is equal to VU plus the shear force that needs to be increased because of torsional moment. VE plus VT I can write. VU plus VT is 1.6 times of TU by P. This is how you can write in this way. Now VE, how I can write this VE, brother? VE is equal to VU. What is that VU, brother? The value of this VU is 20 kilonewton. I can write 20 kilonewton plus 1.6 times of TU. TU is how much, brother? TU is 9 kilonewton meter. So 9 kilonewton meter divided by B, the width of the section. This is 300 millimeter. So in terms of meter, it is 0.3 because I need to use the consistency of units. Here it is meter, here it is meter. These two will get cancelled. The final answer will be in kilonewton only. So if you do, this answer will be 68 kilonewton. So you can pick option D for Detroit. This is how you can do. Ipsita Chowdhury. Hi Ipsita, how are you? Hope you are fine. Right? So can I move to the next question or next problem? Here Ipsita Chowdhury, Dr. Civil Shivam Tiwari. Can I move to next question? Right? Moving to the next question. I hope you are able to see this question. A reinforced concrete beam of 10-meter effective span. So there is a 10-meter effective span is there. Maybe I can show a 10-meter effective span is there. Okay, this is the effective span I want to show you. This 10-meter and 1 meter effective depth. The effective depth is 1 meter. Is simple supported if the total UDL acting on the beam is, what is the total UDL that is actually acting on the beam? The total UDL that is actually acting on this beam is 10 meganewton per meter, right? 10 meganewton per meter. Then they are expecting design shear force. What is design shear force? First of all, can you define? Design shear force is a shear force that has got developed at critical section of shear. Design shear force is the shear force that has got developed at critical section. Can we say in this way? Now you tell me here these are, let us suppose these are supports. Right now the supports are under compression. So due to this beam, supports or columns, whatever that may be, are under compression. When supports are under compression, what I teach you in our previous class in limit state of shear, the critical section for shear is not exactly at the support, I can say, but from a distance of small d from the support, right? So the critical section for shear is at a distance of small d from the face of column. Here the column width, nothing, everything is given. Na? So from this one at a distance of D, I am taking it as critical section. The value of the D is 1 meter. Here I can show in this way. Then it is 10 into 10, it is 100 divided by 2. It is, I can say, 10 into 10, it is 100 divided by 2, it is 50. I can show this section is 50. At this reaction it is 50 meganewton. This is 50 meganewton. I need to find out what is the shear force at this critical section. I just want to show you, this is the critical section for shear. So if I want to find out the shear force at 1 meter, the problem is over. If I take this section is XX, I can take the freeboard diagram of left hand side of a section. Can I take the freeboard diagram of left hand side of a section? This is 50 mega Newton. This is cut section XX, and this is UDL, and the UDL intensity is 10 mega Newton, and the distance is small d, which is 1 meter. Now, what is the shear force here at this section XX? Can you find out what is the shear force at this section XX, brother? Shear force at this section XX is nothing but it is called as design shear force. Ipsita, sir, why critical section is taken at a distance of D? Dear Ipsita Chaudhary, anyway, I will tell the reason. I just want to convey you one thing. Have you completed my lecture of limit state of shear? In that one, with clear description, I told why the section for shear is at a distance of D. It is very simple. Let me tell you. On critical shear, I just want to show you. This is how a beam is there. If you are consistent in my lectures, then you will understand. If you are coming on one day, then you will not understand, because the reasons everything I teach you. But anyway, I will repeat that again, don't worry. This is a column, right. Now this is the support under compression. Now, because of the support under compression, at what angle this reaction force? This is how the reaction force. At what angle the reaction force is distributed in the beam? The reaction force is distributed in the beam at an angle of 45 degrees. Can I say this is from the face of the column? This is how the reaction force is dispersing into the material at an angle of 45 degrees. The load dispersion will takes place. If this is if this depth is small d, if I want to get at an angle of 45 degrees, definitely this will be the critical section, because the shear crack will happen from tension zone. That shear crack that is happening in tension zone, it is nothing but diagonal tension crack. So here, if you take an element here, maybe I can say, if you take an element here, that element is subjected to shear forces in this way, right? When it is subjected to shear forces in this way, this is a pure shear element. If you see the pure shear element, this diagonal is under tension, right? When the diagonal is under tension, here for this element, this is the crack that is possible in this direction. Not These are the normal stresses. The normal stresses value is the shearing stress tau here, right? And as the crack will happen from in diagonal tension mode from tension zone at an angle of 45 degrees in this way. Here, this is how the shear crack will get started in this way, and the failure will happen at a distance of, if this is d, this is 45 degrees, then from common sense or from mathematics, this width from the face of the column must and should be d. Then only this angle of 45 degrees dispersion angle must and should be satisfied, right? So that's the reason why I can say, especially when the support is under tension, right? There is lot of theory I teach you, right? Why this element is under pure shear at this point? Because in case of simple supported thing, at the ends the bending moment is zero. Bending moment is zero, so normal stresses are zero. So these are normal stresses, these are zero. Only shear stresses are there. When only shear stresses are there, the major principal stress will be happening at an angle of 45 degrees with the vertical. From where you had seen this you had seen from the state of stresses, biaxial state of stress. In From your strength of materials, your teacher might have teach you the state of stress of an element at the support, when the support is simple support, when there is no bending moment. In such case, the normal stresses are zero, only shearing stresses are there. This is from strength of materials, you might have already learned, right? So I can recommend you, dear Ipsita Chaudhary, it is better if you come every day regularly. If you listen to the theory regularly, then then there won't be any problem. So I can recommend you to Ipsita Chaudhary. So go and watch limit state of shear part 1 and limit state of shear part 2 with reasons, with sketches, everything I had derived, at what angle, why, the reason I had written there clearly. Okay, dear Ipsita Chaudhary. And to understand this concept, you require the concept of state of stress at a point. which we people call with the help of stress tensor matrix. Okay, right. So go and watch limit state of shear 1 and limit state of shear 2. Okay, Ipsita, right. So that's the reason why that's the reason why the crack will form at a distance of d from the face of the column. Here there is no column width is given, so from the support condition, from the support itself at a distance of d, I am considering. So if you do this one, what is the design shear force? This is the free body diagram, isn't it or not? Can I write this as free body diagram of left of section XX? Can I write that one, Ipsita? Right? So can you work out what is this design shear force? Is that okay? Hmm. 1 second. Let me rub this so that we can work out the answer here itself. Yes, yes. So I hope you know the equations of equilibrium from your fundamentals of engineering mechanics and strength of materials, especially strength of materials and engineering mechanics will emphasize more about these equilibrium equations. Na? So can you work out what is this shear force Vx by writing sigma Fy is equal to 0? So for this free body diagram, if I write sigma Fy is equal to 0, this 50 mega Newton is going up, whereas this total load 10 mega Newton, it is acting over a distance of 1 meter. Na? So this is 10 mega Newton per meter into 1 meter. So it is 10 mega Newton. This 10 mega Newton is coming down. So 10 minus 10, whereas the shear force Vx is also coming down. So minus Vx is equal to 0. This is what I got is by writing this element is under equilibrium. So it should satisfy the equilibrium conditions. Even sigma Fy is equal to 0. So when I do that, the shear force value Vx is equal to 40 mega Newton. It is not in kilonewton. Please understand, it is in mega Newton. That's the reason why the result will also be in mega Newton. So the option is D for Detroit. Is that okay, Ipsita? Is that okay? Right. Can I move to the next slide? Can I move to, I mean, next question? I mean, can I move to the next question? So I think uh, I had completed all the questions in this models in this limit state of torsion. And before I end up the session, I just want to convey one thing like uh, uh, if you are a serious an aspirant of GATE or ESE, dear Ipsita Chaudhary or Dr. If you are a serious aspirant of GATE or ESE, dear Ipsita Chaudhary or Dr. Civil or Shivam Tiwari, if you didn't take any sort of paid course till now, I can recommend you guys to take the paid course, and the course duration will be there from 1 month to 24 months. And I can, if you are a final year student, I can recommend you guys this 12-month course or 18 months course, and the cost after 10% discount is 27,225 for 12 months course. The cost after 10% discount for 18 months course is 34,650. I can recommend this 24 months duration of subscription for the students who are in third year and second year. For third year and second year students, I can recommend this 24 months duration course or duration subscription. The cost is 39,600 after 10% discount. But for any course from 1 month subscription to 24-month subscription, right? If you are really want to get 10% discount, then you are bound. Then you must and should use this code VT10. If you are using this code VT10, it shows your trust on me, right? And shows your faith on me. It will directly connect between you and me, right? And it will directly give you 10% discount on all the courses in Unacademy Plus, not only for GATE and ESE, but also for any course from 6th standard to PG standard that was provided by Unacademy Plus platform, right? And every day my class is happening every day. If you see in this YouTube channel of Let's Crack GATE and ESE Civil YouTube channel, my class is happening every day by 11 a.m. So please subscribe to this Let's Crack GATE and ESE Civil YouTube channel till now if you don't do that one, and please share the same videos to your friends so that they will also get benefited, brother, right? And don't forget to press the bell icon. Please give a thumbs up. Please give likes. Please share this video to more number of your friends so that they will also get benefited, right? This is because this is the free content. And I just want to convey you one more thing. uh, if you want to if you want, if you had some doubts, if you want to ask me some doubts, In such case, for your doubt thing, I already started a Telegram group. So if you come down to my personalized Telegram group, then you are able to ask your doubt. You are able to post your doubts. And the name of the Telegram group channel is Unacademy underscore Civil Engineer Tilak. Here it is that. And if you want to come down to that Telegram channel, use the link which is given below. And in this link, Unacademy U is capital, Civil C is capital, Engineer E is capital, Tilak T is capital. Between Unacademy, Civil, Engineer, Tilak, there are underscores are there. Please, there are underscores are there. So underscores has got merged with this underline. So please be careful about that one. And please come down to this channel. If you are able to post your doubts, I will take care of your entire doubts. Okay, especially if it is from structural background. If it is from non-structural background, then the other faculty who are on the platform will take care of your doubts, brother. So finally, I want to say one more thing. Please give a thumbs up. Please share the same video to your friends and to your teachers also who are interested. So thank you very much. Thank you, and please subscribe to our channel. Let's crack GATE and ESE, and don't forget to press the bell icon. If you press the bell icon, notifications will come to you, and you will not miss even a single lecture also. Thank you. Thanks. End of the session.